Okay, so today we're looking at how we're going to name ionic compounds. All right, for those of you who are following along at Fairfax, this is using page 5 out of our notes, naming ionic compounds, so it's right there. Well, so what we got to do first is figure out just what is the deal, what are we working with in terms of our ions. Okay, and so those are all based on the basically the main block elements, the S block and the P block elements that we see. And I'm going to grab a periodic table so we can see those to look at. So for our main block elements, we've got the S block. Okay, we've got the S block here. We've got the P block over here. And we like those guys. We like them because they're very predictable in terms of how they're going to react. We've actually put together a chart using some of the S and P block elements here, okay, which we've zoomed in on. And the reason they're so predictable is because they've used a number of valence electrons to decide how they're going to react. So let's go ahead and look at some of these guys. We got hydrogen, lithium, sodium, potassium, rubidium, cesium. Every single one of those elements has one valence electron. So with the one valence electron, we know how they're going to react. They want 8. Now, these got a choice. They can either pick up an extra 7 valence electrons, or they can somehow lose the one they have and drop down to the next energy level below. Well, we know that these guys are very lazy, so these guys are going to drop their 1 valence electron and end up with a charge of +1. So again, oxidation state just means the charge that it's going to want to take after it reacts. If we jump all the way over here to the right, we see helium, neon, argon, krypton, xenon, and radon. Those are the noble gases, and they are happy because they already have 8 valence electrons, which means they're not going to need to react. They don't need to have a charge to be happy, fulfilled, and all that. Well, so let's go back and fill these in as we go. The halogens, fluorine, chlorine, bromine, and iodine, all have 7 valence electrons, so they only need to pick up 1 more. They're going to gain 1 electron and end up with a charge of -1. So when we see fluorine, chlorine, bromine, and iodine in an ionic compound, try saying that bunch fast, in an ionic compound, they're always going to have a charge of -1. Oxygen, sulfur, selenium, and tellurium all have 6 valence electrons, so they need to gain 2. Nitrogen, phosphorus, arsenic, and antimony, when they are in a ionic compound, they're 5 valence electrons. They are going to gain 3 electrons to end up with their 8. So these guys in an ionic compound will always have a -3 charge. Carbon, silicon, germanium, tin, and lead, well, really just carbon, silicon. The rest of these guys, they act a little bit strange, so we'll see them later. But they have 4 valence electrons, which means they can either lose 4 or gain 4. Either way, it's pretty much the same to them. Boron, aluminum, gallium, indium, and thallium, they've got 3 valence electrons, which means it's a lot easier for them to lose their 3 than it is for them to try and gain an extra 5. Lastly, beryllium, magnesium, calcium, strontium, and barium, with these 2 valence electrons, it's a lot easier for them to lose 2. So this is the main block, and we like these guys because they make everything so very predictable, okay, in terms of how these things are going to react. So let's zoom out a little bit and figure out how we're going to name some ionic compounds. Okay, I'll give you a couple examples. We'll scoot this page out of here. We'll come back to it later. So, a couple examples. Let's take a metal, Mg. That's magnesium. And let's take a nonmetal. How about S? That's sulfur. Well, the name for the compound that happens, sorry, let me go ahead and label my, my data here, metal and nonmetal. The name for the compound that would happen when magnesium reacts with sulfur would be magnesium sulfide. Let's see what happens with that. The magnesium stayed magnesium, sulfur became sulfide. Let's see another couple. Let's see if that changes at all. Let's use Al, that's aluminum. And let's say it reacts with F, fluorine. Okay, so the name for that one would be aluminum fluoride. So we go from fluorine to fluoride. Aluminum stayed the same. Let's see one more and see if we can't figure out our trend here. Let's use Na, that's sodium, and how about oxygen? That's O. So this would end up making a formula, or making a compound called sodium oxide. Oxygen becomes oxide. We're going to come back to these three, but let's get the prime way to name ionic compounds. We're going to take the name of the first thing. Say we got NaO. We're going to take the name of the first thing, that is sodium, just its name. We're going to take the name of the second thing, which is oxygen in this case, except we're going to change it. It becomes oxide. Cut the ending off and add an "ide." Na2O, sodium oxide. MgCl2, that's magnesium, and chlorine becomes chloride. So this is magnesium chloride. Very, very simple for all of these main block elements. All we've got to do, give the name of the first thing, give the name of the second thing, except cut it off and replace it with "ide." So if we have something interesting, let's say, ooh, how about this? Ca2C. That would be calcium. Carbon would become carbide. So Ca2C would be calcium carbide. And that's all there is to it. Now, let's go ahead back to these guys up top. We not only need to know what their names are, but we need to know their formulas as well. So we're going to talk a little bit more in depth as we move on to as we get. Excuse me. We're going to talk a little bit more in depth as in a way to do this a little bit easier. But let's see if we can't figure out how to write these guys' formulas. Excuse me. Aluminum, we know, wants to be a +3. Okay, we take a look at our chart previously. We wrote previously. We find aluminum here, and it wants to be a +3. We find, what's our other one? Fluorine. We find fluorine here, and it wants to be a -1. Well, here's the deal. When ionic compounds form, the idea is not just to attract positive and negative, but to cancel them out. So these three positives somehow need to get balanced out by an equal number of negatives. If I've got three positives coming from aluminum, I'm sure you can tell me how many fluorines each I'm going to need to balance that. Aluminum fluoride would look like this. Al, 1 aluminum, F3, 3 fluorines. Let's try the same thing up here. Magnesium, we know, wants to be a +2. Sulfur also wants to be a -2. Well, we've already got Mg2 plus, S2 minus, 2 and 2. It balances out. We just need 1 Mg and 1 S. Take a look down at the bottom. Na, sodium, wants to be a +1. All right, we know that it's got a 1 valence electron, so it's going to lose its 1 valence electron and end up being a +1. Oxygen and sulfur are both in the same group, so they both have 6 valence electrons. When they react, they're going to try and gain 2 more and end up being a -2. So oxygen here with a -2. Now I've got 2 negatives and only 1 positive. So I'm going to need to increase my number of positives, have 2 of them to make up for my 2 negatives from the oxygen. We're going to learn a much easier way of doing that, but that's kind of the idea behind where these formulas are coming from. Let's see a couple examples off of the same worksheet that we were working on earlier. Just run through these a little bit quickly. Pick out the big bad ones and move from there. So, how about Mg3N2? Zoom in a little bit so we can see this. Mg3N2. Well, Mg is magnesium. N is nitrogen, so nitrogen would become nitride. Now, there's no real rhyme or reason for how we decide where to cut this thing off. It could be nitroide or nitrogide or nitride, Nitride sounds the best, and so it's the one that's accepted. Generally, you're going to find the one that has the best flow is the one that is accepted to use. Okay. Since we've already done the work for N, why don't we look at this one? Rb is rubidium. And again, we know that nitrogen turns into nitride when it's at the end of the compound. Now, we're sitting here and thinking, wait, Mg3N2, Rb3N. Don't we need to do anything because there's different numbers of elements there? Well, it's a good thought. But when we say magnesium nitride, we automatically know that magnesium is going to be a 2+, nitrogen is going to be a -3. The only way that they combine so that they balance out charges is with 2 nitrogens, each at -3. So let's follow along at home. That's 2 nitrogens, each at -3. 3 magnesiums, each at +2. We get a +6 here, and we get a -6 here. It's the only way they're going to balance. Take a look at here. Rubidium is a +1. Nitrogen is going to be a -3. We know we need 3 rubidiums to balance out the 1 nitrogen. So just by saying rubidium nitride or magnesium nitride, we know everything we need to know about the compound. Let's take a look down. Let's see, what ones haven't we done yet? Here, how about this one? CS2Se. CS is cesium, and Se is selenium. So selenide would be the way we'd write that one. Last one. We'll do this one. Magnesium iodine becomes iodide. That's all there is to it. Let's add a little wrinkle now. So on the back of this page, zoom back out a little bit so we can get the whole page in. There we are. We've only been dealing with the main block. Here's the problem. Transition block isn't nearly so well behaved. So let's grab our periodic table here. The elements between here and here are all, well, they are not quite as neat and orderly as the main block elements. And even we'll include a couple of the ones over here, especially tin and lead. They're really not all that well behaved. They don't act like carbon and silicon like they should. So, transition metals can all have different charges, which makes things a little bit difficult when we're trying to write some formulas or determine even the name. If we take a look down here, we've got 2 different combinations of copper and chlorine. So let's take a look. This copper and chlorine. The way we're going to figure out these names, we've got several steps. We're going to write the name of the metal ion and the ion it's bonded to. Well, that one's easy. Cu is bonded to Cl. So that is a copper chloride. The problem here is that down in this example, we can also call this copper chloride. Whatever are we to do? Let's take a look and see how we're going to differentiate between these two. What we need to do is figure out what the charge on this copper is, okay, and what the charge on this copper is. That's going to tell us the difference between these two types of compounds. How we're going to do that? We're going to find out the total negative charge of all the ions that the thing is bonded to. I know that chlorine is a -1. Chlorine wants to be a -1. However, there's not only one chlorine. I see 2 of them here. So I'm going to have to figure out the total amount of negative charge. Each chloride is -1. There are 2 of them. So I'm going to multiply that by 2 and find out a total negative charge of -2. The cool thing, however, is that that's balanced by a +2. That's our total positive charge. What we want is to figure out the charge on each individual copper ion. So I'm going to take my +2 total positive charge and divide it by the 1 copper atom that I see. I'm going to split that +2 charge evenly among all of my coppers. Well, I get a +2 divided by 1. 2 divided by 1 gives me a +2. This number goes into a Roman numeral in the middle, telling us that this copper has a +2 charge and it's bonded with chlorine. copper 2 chloride. Let's see how that's different from regular old CuCl. In this case, chlorine is still a -1, but there's only one of them. So my total negative charge is only -1, balanced out by a +1 as my total positive. The total positive and total negative are always going to be exactly equal and opposite. I'm going to take my +1 and I'm going to divide it by the 1 copper that I see and get an answer of +1. That means that each copper atom here, each copper ion, has a charge of +1. So we have the difference between copper 2 chloride and copper 1 chloride. I'm going to show you 2 more examples, and then we'll do a couple that aren't on this sheet. Let's look over here, NiBr4. This is a nickel. Bromine becomes bromide. Each bromine has a -1 charge, and there are 4 of them. All that means is that we have a total of -4 and a total of +4. I'm going to divide this up a little bit so it doesn't get quite so confusing. Divide it by the 1 nickel that I see, and I get a +4. That +4 becomes a Roman numeral, nickel 4 bromide. One more. This one actually has multiple metal atoms. So let's see how it's going to work. Au is gold, and S is sulfur, so in this case sulfide. Each sulfur wants to be a -2, okay, because it's got 6 valence electrons. It's going to gain 2 of them, okay, to make 8. Now here we have 3 individual sulfurs, which means that my total negative charge is -6. That's balanced by a total positive charge of +6. So I'm going to take my 2 golds and divvy that up evenly. Total positive charge of +6 divided by 2 Au gives me each one having a charge of +3. That means that each gold atom, each gold ion, has a charge of +3. Gold 3 sulfide. We're going to take a look at 1 or 2 other examples with the transition metals. We'll blow them up nice and big. We'll even use the periodic table here so we can identify some of our metals. Let's try this one. How about chromium and 2 phosphorus? So here we would have a chromium, and phosphorus becomes phosphide. Well, here's the deal. Phosphorus wants to be a -3, and there are 2 of them here. So we've got a total negative charge of -6. Transfer that over. It's a total positive charge of +6, but we only have the 1 chromium, which means that that 1 chromium has a charge of +6, positive 6. So this would be chromium 6 phosphide, pretty highly charged. Take a look at one more example. How about we look at this one? Let's use, how about molybdenum? And we'll say it's MO2S. Well, we know, okay, molybdenum, there we are. Molybdenum, and S is sulfur, so becomes sulfide. We know that sulfur over here has got 6 valence electrons, so it's going to want to gain 2 more and end up with a charge of -2. Well, I only see 1 sulfur here, so my total negative charge is only -2. Total positive charge is +2, but I've got 2 molybdenums. I need to divvy this one up evenly. So I'm going to divide by my 2 molybdenums, and I'm going to get a charge of +1. That means that each one of these molybdenums has a charge of only +1. This would be molybdenum 1 sulfide. Okay, so that being said, There are 5 different elements in the transition block. 5 different elements in the transition block that actually do behave. They are in order: scandium, yttrium, zinc, cadmium, and silver. Scandium, yttrium, zinc, cadmium, and silver. When you see those, they will always, always, always have the same charges. Scandium is always a +3. Yttrium is always a +3. Zinc and cadmium are always +2. Silver is always +1. You will have to know those. Now, on the flip side, the transition metals, so everything else in the transition block, you need to know and need to be able to calculate the charge for. There's also 2 other little scoundrels this way, tin and lead. Tin and lead, that also are going to need transition metal Roman numerals. So transition metal compound or tin or lead. They will both need Roman numerals when you name them. Okay, so we're going to jump on and do one additional piece, and then go ahead and learn how to, that's not right. We're just going to go ahead and learn how to write the formula for an ionic compound, and that's going to happen in a separate video. So check out the next one in the series.